Actually, the BJ structure is the old one, which you shown. It's Intel. So now they have deprecated and they make it clubbing into the PCH chipset, platform
Okay.
control hub. North and South has.
Yeah, here we have chipset and monolithic multi-chiplet. There are different models.
Yeah, due to
That
latency
this diagram
reduction.
is
Yeah.
old one. Whatever I shown
Yeah.
North Bridge, South Bridge, that is old. But whatever I showed SOC, that is present 2023 SOC only. We
Yeah.
use the
Got.
price.
Yeah. To
Okay.
the reducing the latency only they have deprecated because every time any component first South bridge, then North bridge, then CPU, there is a time consuming, right? So they have deprecated and make it one.
Okay. Okay. So everyone understood now what is the difference between serial and parallel? Clear? Who asked the questions? Aditi, Jacob, Lahari, Manoj, Murlidhar, Narayana, Ranjit, Roshni, Sagar, Shubham, Tarun, Vinita. Any doubts?
No, no.
Ma'am, in the last part, what you said, na, like non-coherent and coherent, can you explain that part once? The what is the purpose of use coherent and non-coherent? For
Coherent and
transmission.
non-coherent is related to where we use processors and non-processors just to differentiate between non-cores and normal functional blocks. We just use the coherent or not, just to differentiate that. Okay, both connections will be different to the data fabric, so that's why we will differentiate that. While we are designing, all coherent will be one side, non-coherent will be one side. So while you are writing the test cases also, there will be signals if you see in same block diagram, there will be lot of configurations. CPU related configuration, graphics related configuration, NBIO related, SBIO related. There will be a lot of configurations, right? So every time whenever you write lakhs of test cases, we cannot write different for each test case. We can't assign a separate configuration. That's why all PCIe related comes under one config. All core related comes under one config. In core also we will have MP1, MP2, CCX1, CCX2, even nowadays CCX and IOD both, we are getting two types. So to define everything separately, we divide like that, different configurations and coherent, non-coherent like that. Okay.
Okay.
So clear everyone, the UART communication from computer 1 to computer 2. Within a computer, everything we do the parallel communication, but whenever we are communicating outside, we use a serial communication. That's why we are converting parallel data to serial data, UART 1 to UART 2. And this is what the frame format. Here we don't have any addresses. We just have start bit and stop bit and data transmission between each other. And last PB is the parity bit. If any error is there, it will detect the error. Okay. Next, this is what the top level block diagram for UART protocol. Top level will have UART receiver, transmitter, and baud rate generator. These three we need to design in RTL. Next week we are going to design these three in RTL using Verilog HDL. Today we will complete the block diagrams. We'll try to understand the block diagram of each. So this is what the transmitter block diagram. There is a FSM first of all. FSM will be getting TX start bit data. and this TX data will be coming from the before master. There will be master here, right? Before like APB or APB master will be there, or slave. That slave data will be getting to this master. Okay. So how we write the FSM? So this is what the transmitter FSM. We need to design the transmitter FSM in Verilog also. Okay, first of all, every final state machine will have a ideal state in initial state. So ideal, and then start bit. Start bit in the sense just a exact frame format you need to put here. Start bit, data, parity bit, stop, exact frame format. So start bit, TX start data is high, and then data 16x baud rate. 16x baud rate in the sense of how we calculate the baud rate and division we will discuss. Here we are passing 8-bit count data. So here your limit is 8-bit data. Okay. Once 8-bit data is transmitted, then it will go to the parity bit, or else it will be repeating loop. The count until equal to 8, it will be in repeated loop. Why? Because we need to transfer 8-bit data. For 0, 1, 2, 3, 4, 5, 6, 7 case, it will be in a same loop. So once it reach count equal to 0, so we have transmitted 8-bit data, then it is going to the parity bit. It will be checking the parity here, whether it is error or not. In transmitter side, we don't check the parity error. In receiver side, we check the parity error. So here it's a parity bit, and under 16 baud rate, we are sending to the stop bit. Whenever stop bit is 0 or high, based on your design specification, it will go to the stop state. Okay. That is what transmitter FSM. From the FSM, the data is sending to the PISO, parallel input, serial output. And from here, the data will be sending to the multiplexer. Multiplexer is a 4x1 mux here. 0, 0, 0, 1, 1, 0, 1, 1. 0, 0 means a start bit. 0, 1 means data bit. 1, 0 means stop parity bit. 1, 1 means stop bit. So based on the selection line, it will be selected any one of the functionality and sending the data out. Parallelly, the parity bit will be checking here based on the transmitted data and load data. TX busy. If you want to send any transfer again, if TX is busy state, then it will indicate that transfer is going on. So it cannot accept second transfer. Once busy is completed, busy state is disabled, then we can transfer second one. Like that receiver side, here we will get the receive input. We just send the read data and detect start. If start bit detected, then send to the receiver FSM again. Here the data will be converted from serial to parallel, and parity checking will be there. Stop bit checker also will be there. Just try to understand the functionality, how the signals, suppose the arrow, how it is sending from here to here. You have 1 week time to revise you need to practice the program also. Okay. And final state mission, same here. In a transmitter, we didn't check the parity, right? Ideal, start bit, detect, data. Still count is not equal to 8. If count equal to 8, it will check the parity bit. We need to write the program for parity. Can you tell me which logic we write for parity detection in digital logic design? Simple logic. How you will write a Verilog code to detect the parity?
XOR.
XOR?
For even parity, it is XOR. For odd, it's XNOR.
Okay, good. Okay, then you can able to write the program also then. So here it will check the parity. If any parity error is getting, it will indicate the error and just go to the ideal state. In your protocol, it just detect the error, but it doesn't correct the error. Okay, so this next if there is no any error, it go to the stop bit to ideal. Okay, so this is how we write the FSM in your and transmitter. Everyone understood? I will share the PPT also. Just go through the PPT. So your transmitter, in your transmitter, what are there? Final state machine, piezo, parity generator, multiplexer. So you need to design mux, parity, piezo, FSM, and top level you need to connect all DUTs. And now design separately. First mux, how you will create the mux 00011011. And then parity, how you will write the parity checking. You just told XOR gate, right? Just write your own code first, then we will discuss. Next FSM. FSM is given clearly. Even system Verilog students also can write. We already discussed how to design FSM. So you can write the same final state machine program here by next week. And then next one, parallel in serial out. For parallel in serial out, you can write any of the program like in simple way, or if you want to write in a complex, you can prefer anything. And just and then your receiver. In your receiver, what blocks will be there? Start detector, CPO, parity checker, stop bit checker, receiver, FSM. Same. Detect starter, CPO, parity checker, stop bit checker, FSM. Write the program for this. Detect start. When it will detect the start, when our receiver input is 0. Then start bit detected. Once start bit detected, it will send the data. So next, CPO, serial in parallel out. So what is the simple logic for serial in parallel? Next, parity checker completed. Stop bit checker also you need to. When in which case the stop bit is high and start bit is high. And receiver final state machine. Same like transmitter FSM. And one of the major thing is BRG, baud rate generator. Baud rate generator I have given here clearly. Just go through the example here. Try to understand the baud rate generator. If you, we will discuss in the next week anyway. Okay. So what you will do in this whole week? Go to entire specification of UART. Try to understand the this frame format and the communication and top level block diagram. Your transmitter, receiver, FSM, baud rate generator. Everything try to understand. I will share you the interview questions also, assignments. Okay. In the next session, we will discuss this entire RTL design and also baud rate generator. Okay. Whoever know UVM, I will give you the UART in UVM also. Others, you just complete in Verilog. Okay. Any doubts for today's session?
Can you send yesterday's PPT also? We didn't get it.
I will share it and I will share the recorded sessions also. Others, any doubts from today's session? We will discuss baud rate also. Wait, we'll complete till here. What is mean by baud rate? So what is mean by baud rate? I already told, right? Baud rate in the sense, just instead of using clock in the UART protocol, we use the baud rate generator. That means to make the synchronization between transmitter and receiver, right? So it just determine the speed of data transmission, which is measured in the bits per second. How can we calculate the baud rate? Baud rate is nothing but clock frequency divided by baud rate division. You may get the doubt. Here we don't use any clock, right? Then what is meant by frequency? Frequency in the sense here, there will be no common clock between the transmitter and receiver, but there will be a frequency. Frequency of transmitter will be there, frequency of receiver will be there. We need to match both the transmitter frequency and receiver frequency without connecting any clock. By using the baud rate, we need to match both the frequencies. Okay, so that's why baud rate is equal to clock frequency divided by baud rate division. We need to calculate the divisor also. Okay, so how can we calculate the baud rate here? Suppose any system frequency like 16 megahertz, 20 megahertz are there. So first of all, we need to determine the baud rate divisor of UART internal registers, and we need to apply the above formula. Okay, suppose example, if you see here, we already have standard baud rates. Actually, we no need to create the baud rate. So these are the standard baud rates like 110, 300, 1200, 2400, 4800, 9600, 1200. These all are standard baud rates. Okay, but still if you want to calculate, then how we can calculate in the sense, suppose system clock you have taken as a 16 megahertz, receiver side and also transmitter side you have taken as a 16 megahertz, and baud rate divisor is a 16. 16 is mostly fixed at receiver side and transmitter side. Mostly we use 8-bit data, 8-bit data, right? That's why 16 is constant mostly. And then baud rate, how we will calculate the baud rate? Clock frequency divided by baud rate division. So clock frequency is a 16 megahertz by 16. So baud rate is a 10 lakh BPS, bits per second. Okay, so that is how we create 1000000. Like that, if you see here, standard baud rates maximum 57600, and here 115200, and higher baud rates also available based on the versions of UART. Okay, so if you see here, the divisor is usually set in a UART register. Example, DLL and DLM. Can you tell me what is a DLL and DLM? Divisor latch low byte and divisor latch high byte. Okay, that means low 8 bits comes under DLL. Upper 8 bits of the divisor comes under DLM. Okay, so based on this lower bit or lower byte, 8 bits, right? Commonly 8 bits. So lower byte and higher byte, both are combinedly we call as a 16 divisor. So that's why mostly 16 we put for divisor. Okay, so see here, calculate the baud rate divisor. The baud rate in UART determines the speed of the data transmission measured in bits per second, calculated in divisor clock frequency, and the clock frequency is 1648 and baud rate is 9600 or 115200. Then what is the divisor? 16 is a fixed value in a standard UARTs, mostly 8-bit data we transmit, right? Transmitter plus receiver. So that's why 16 is mostly fixed in all type of UARTs. Based on divisor, how we can calculate for 16 megahertz? What is the formula? Divisor is equal to clock frequency by 16 into baud rate. Okay, so these are some of the specification. So if the system is 16 megahertz clock and the baud rate is 9600 bits per second, then what is the divisor? Is 104. Suppose 16 by 16 into 9600. So 16 by 153600, it's 104. Mostly division must be in integer, right? That's why round off to 1. not 4. Okay, like that we can calculate divisor and baud rate in this case. So example 2, 48 megahertz divisor, um, 48 megahertz clock, 1152000, that is fixed baud rate. Then what is the divisor? If divisor is 26, then what is the baud rate? Baud rate is 11585384. And there are some of the examples to calculate the baud rate. Just try this. Okay, next week we will discuss more clearly about the baud rate. Did you understood everyone what is meant by baud rate? Based on this value only, we are going to transmit the data between transmitter and receiver based on the clock frequency. Try these 3 examples. Example 3, 4, 5. For 20 megahertz clock, standard baud rate is 83400. First, calculate the divisor. Okay, divisor means clock frequency by 16 into baud rate. Based on that, calculate the baud rate again. Okay, approximately you will get the same value. And for clock also, you need to create the baud rate. So transmitter side, receiver side, if both frequencies, if you consider, mostly we will consider same frequencies, right? Based on same frequencies, so what will be the baud rate we need to calculate. But there are a lot of limitations with the UART baud rate because a lot of mismatches will get using this method. So later on we move to the clock, main clock, will connect the clock to the transmitter and receiver. Those all are additional features. Okay, understood everyone till here? Any
Ma'am,
doubts?
I have one doubt.
Yeah, tell me.
Ma'am, this clock frequency, you're telling when sender and receiver are working on the same clock frequency. What if they are in different frequency? I mean, is that even a case? I'm not sure about it.
If it is a different actually we need to make sure both will work with at a high same frequencies only. But small mismatches will be there. If there are mismatches in the frequency, what happens? One will be work at a higher speed, one will work at a lower speed. So majorly we see the data loss, right? If one transmitter works at a high speed, if receiver works at low speed, data loss will be happen, data mismatches will be happen. That is what the errors we will find.
So initially you mentioned the disadvantage of that only that there is a baud rate mismatches. Is it because of that only?
Because of baud rate only.
I mean, because of different clock frequencies?
Yes. Even if you take same clock frequency, while we are calculating the baud rate, we may get the difference, right? Based on the divisor values or based on the these baud rate values, we will get the different. And also frequency will be not standard at the transmitter side and receiver side. Okay, so that's why we will get some little frequency mismatches.
Yeah, okay, ma'am.
Others are, yeah, know that. And also I'll share this recording to understand how. So some interview questions on UART. Yeah.
Thank you, ma'am.
Thank you.
Thank you, ma'am. Thank you.